also see me?
Yep, you're all good.
Oh, that's good. Glad to hear it. Okay. So today I want to talk about the halting theorem. And we'll introduce two new proof techniques, dovetailing and diagonalization, which we will use in the class and you'll use in the future. So in this lecture, I'm going to explore with you the far reaches of what computers can and cannot do. And in doing so, we're going to prove the single deepest result in computer science, which is Alan Turing's halting theorem. And this is closely related to Gödel's incompleteness proof, which really turned mathematics and science on its head in the 20th century. And we'll, among other things, we'll talk about different sizes of infinities, bigger and smaller infinities. And at the end, if there's some time, but certainly in problem set 4, we're going to relate it all back to compiler optimizations. So it's not all theory. So the context of this is that we've been showing you some super powerful programming tools. And you might think that given those, that computers can solve any problem, just given the right program and perhaps the right input. And if you thought about this for a little bit, you might realize there could be difficulties with solving, for example, social or philosophical or religious problems. So maybe you might think that computers can only solve every mathematical problem. But even that is not true. And today we'll look at some things that can't be computed, and I'm going to prove they cannot be computed with your help. And they can't be computed no matter what program, what language, what machine, how long you wait, or anything. And I think these are not only comprising the deepest result probably in computer science, but the halting theorem is arguably the greatest intellectual achievement of the 20th century. And what's remarkable about it is that you can understand it and prove it rigorously after only a few weeks of CS230. So really every intellectual should know this, and every functioning member of society that wants to understand technology. Incredibly important indeed. So I don't always write out exactly what I'm hoping to convey, but I did and put them in the notes this time, which are on the web, because I think that the wording of this is super important. I'm going to annotate it a little bit as we go along. So why is it that there are things that are uncomputable no matter what you do? Well, we're going to look at two reasons here. So one reason is that there are more mathematical functions than there are programs. Actually, there are lots more. And bizarrely, although you'll get comfortable with this soon enough, there are infinitely many of both, but there's a bigger infinity of functions. And I'll even show you a function that it would be contradictory to compute. So it's, in other words, it's an explicit counterexample to the claim that everything is computable. This is really quite remarkable, and we can do that at this point in the class. So some desirable compiler optimizations are uncomputable, right? So this isn't just a math problem, but it is at its heart mathematics that we're going to be talking about. Now, here's how we're going to approach this as we go ahead. So what we're going to do is first we're going to show that there are countably many programs. Now, a lot of terms in mathematics do mirror terms that we have from Common English. And if it jives with your intuition, that's fine. Otherwise, it's a definition of a technical term. But for something to be countable means you can give everything in the set an integer. So there are countably many programs, you can give them all integers, but then we'll show that there are uncountably many functions. There's so many, it's impossible to give them all integers. You run out of integers, basically. And that means, as a consequence, that there must be some function that is not programmable. Pretty remarkable conclusion when we think about this. So there's some function that isn't programmable, and we can prove more than existence. I can show you a particular uncomputable function, a function you would like to have, or at least you might be assigned to get, but you can't actually write a program to compute it. So we're going to use proof by contradiction, and that's why I wanted you to have a solid grounding of that before we entered this class. But we're also going to show you a new technique that's related to this. It's actually a form of contradiction in some sense, called diagonalization. So note some terminology. You won't know this till the end of class, but there are two new proof techniques today: dovetailing and diagonalization. And they're different. Students sometimes get these confused. And of course, we'll give you lots of help in understanding what these mean. All right. So the first thing I'm going to do is I'm going to work with you to show that the set of all scheme programs is countable. And again, we're going to say a set is countable if there's a way to number the elements of the set. So for each integer, there's an element of some set S. Now, I've written this all out in the lecture notes for you, and I'm going to go through it, but this is easier done by writing it out as mathematics on the document camera, so I'm going to do that instead. But all the notes are there if you get confused or there's a handwriting problem of some kind. All right. So let's write some of this out, some definitions. So definition, a set S is countable if there exists a function that has the property onto from the natural numbers onto S. So this notation means the input type of the function is a natural number and the output type is whatever your set is. Now, you may not know what an onto function is, although there are some notes about it, so I'll define it here, and we'll do much more of this in the next few lectures. So define, what does it mean for a function to be onto? F is onto if for every element little s in S, there exists some integer n such that f of n equals s. So in some sense, you can think of this, I mean, how do we think of this? You think of the function covering s. Now let's do some examples to try to think about this. Examples. Well, the natural numbers is countable, n. Why? Well, just take f of n equals n. So trivially, we can give every natural number a number. Something more interesting, the set of all integers, including the negative ones, is countable. So there are various explicit formulas for this, but one that I like to do that actually completely defines this is to say, if you have an even number, we're going to send that to n. If you have an odd number, we're going to send it to minus n. So that's our definition of function. So now we know that the integers, including the negative integers, are also countable, which is pretty neat. Now we've also talked about the rational numbers. Remember, with rational numbers, we could define as the set of all fractions, a over b, such that a and b are integers and b is not equal to 0. So actually, the rational numbers are also countable. And here's the argument for that. So I'm going to imagine writing this out in an enormous infinity by infinity table, or at least define the table implicitly. So I'll do something like this: 1 over 1, 1 over 2, 1 over 3, 1 over 4, 2 over 1, 2 over 2, 2 over 3, 2 over 4, 3 over 1, 3 over 3, 3 over 2, 3 over 3, 3 over 4, 4 over 1, 4 over 2, and so forth. So this goes off to infinity in every direction. And what I want to do is I want to assign an integer to each of these rational numbers in some order, and I'm going to do that by what's called dovetailing. And the way I'll do it is like this. So I'll show you the order by circling these, and you can work out what the mapping actually is. That's the first one, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, and so forth. And as an exercise, you can work out the order And this process is called dovetailing. It's a constructive proof technique. You're proving something exists. So f of n is the rational that's occurring in that order. The term dovetailing actually comes originally from carpentry. So if you all make anything out of wood, you might know that. So all sorts of things are countable, even surprising things like the rational numbers, because there are a lot of rational numbers. But there are things that we can't count as easily, as we're going to have to deal with that. So let's see, what do I want to do next? I think what I want to show next is that there are countably many programs. So this is an interesting argument. Let's do it. So remember, all programs are finite. So all programs, say in Scheme, are finite strings of, say, ASCII characters. So my claim is that there are countably many programs. Why is this true? Well, there are countably many programs because there are countably many finite strings over an alphabet. So suppose we use our regular alphabet. I won't use funny symbols and punctuation, but we count like this. A is 1, B is 2, C is 3, and so forth, up to 26, which is Z. And then we'll use 27 for the string AA, and 28 for the string AB, and so forth. So we can assign an integer to every finite string of ASCII characters this way. Now, not all of these are legal Scheme programs, but all Scheme programs are clearly on this list. So clearly there are only countably many programs in Scheme or any other language. So that's pretty amazing. You know, in a way, we can count the programs, which is kind of nice. But herein a problem arises. And the problem is that there are only countably many programs, but there are uncountably many functions. And this requires a proof because it's sort of remarkable. So let's think about that a little bit. So claim. The set of all functions is uncountable. So here's where we prove it. It'll be proof by contradiction. We'll use a slightly new technique. So I'm just going to look at the set of Boolean functions, which will be sufficient. So set S will be the set of functions, say G, such that G takes as input a natural number and gives back true or false. So that's the set. I'm wondering if I can assign an integer to every function in the set. So any element of S can be thought of as an infinite sequence. And that infinite sequence shows the output of S for each integer. Alternatively, you can think of an element of S as being a stream, right, of trues and falses, where the nth element is the value of the function on the integer n. So in other words, I can imagine writing the inputs like this, which will be 1, 2, 3, 4, 5, 6, out to infinity. And I'll put the odd function here. And odd is going to say true, false, true, false, true, false. I have the prime function here. And that's true, 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 false, true, false, etc. Again, another enormous table like this. So the key thing is that S is the set of all Boolean functions. I can think of each Boolean function as a stream, or alternatively an infinite sequence of trues and falses, where the nth element is telling me what the value is on the integer n. So now I can arrange these in a big table like this, where the table going down horizontally, the rows, each row is a different function. And as I go out, the columns indicate the value on an integer. Now I'm wondering if this is countable, right? I'm wondering if it's countable. So remember, countable has a very strict mathematical definition. So I'm going to say, suppose S countable. Right? I'm going to do a proof by contradiction here. So by our definition of countable, if it's countable, then there must exist an onto function that covers it. Then there exists some function f from the natural numbers to S, which has this onto property. Onto meaning no matter what I pick in the set S, say little s, there's some n such that f of n equals S. That's the definition of onto. So now what I can do is I can arrange the elements of S into a sequence that contains all elements in S, effectively sorted by F, and somehow show that F cannot exist by getting a contradiction. So basically, what I'm saying here is that if S was countable, then there's this onto function F, and F effectively sorts the function by their number, their image under F. So this gives me a supposed enormous list of functions. And I'm going to show that supposed list actually can't possibly contain all functions, even though it was claimed to. So here's the way that we would do that. So first, I want to just ask a question to make sure we're on the same page. So look at this function. So we're supposing S is countable, and we assume that there is an onto function from the integers to S. And I want to do some things here. Let me just make sure we're on the same page. Suppose I take F and I apply it to 1. I get something back. What type is this? What do I get back when I apply F to 1?
A procedure?
Say again?
Is it a procedure?
Yeah, I mean, it actually will be what we call a function. Procedure is the right idea, but it's a function of type G up here. So if I interpret your question as being a function, it'll be fine. Is that good? So like a mathematical function, it's of the same, it's of the type here like this. So I'm sort of making a distinction here between mathematical functions and a procedure being something that I could program, because we don't know that we can program them yet. Right, so the value f of 1 is a function. So what I can do is I can use f to just arrange the functions like this. So first function, second function, third function like this. And I suppose I suppose that it's countable, so therefore there is some function like this. Now I can write down the behavior of these functions. Remember, f1 is something like type odd, something like odd. f2 is something like prime, and so forth. f3 might be even, that kind of thing. So I can show the behavior on output just as I did before. 1, 2, 3, 4, 5, and so forth, going out like this. And it doesn't matter what these are, I'll just make up some values. So, because I don't know what these are. Suppose f of 1 looks like this, t, f, t, f. And suppose f of 2 is the function that returns false, at least for a while. And f of 3 goes f, 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 t. And f of 4 goes t, t, f, t, like that. And of course, these go on forever in the horizontal dimension this way because the integers are infinite. And it goes on forever in the vertical dimension because they're an infinite number of these functions. So here's what I'm going to do. Here's the scheme that I'm going to do here. Is I'm going to show that there actually is no such f. In other words, the thing that can't be true is the existence of this function f, and therefore f isn't actually countable. It's kind of remarkable. So more precisely, what I'm going to show is that for any supposed list that an adversary gives me, or a student that's trying to beat me, I can show that I can get you to certify that you have to promise your list is complete. Say, here's your list. Bruce, this is the list. Everything's on it. I guarantee it. I've double-checked my work. I have to show you that no matter how much you promise or what you give me, there's always functions that aren't on the list. So it's possible to construct an element of S that's not on the list and hence the function F is not actually onto. So I'll do that as following. I'm going to look at the diagonal here and look at the behavior of this. So this behavior describes basically the behavior of function I on input I. And what I'm going to do is I'm going to construct a new function like this, which I will call R. And R does this. It does the opposite of the diagonal. So R is going to do false, true, true, false, and so forth. And that's its behavior on 1, 2, 3, 4. So look at this creature. It's kind of a strange beast that we have here when we do this. So basically, for any such table, I'm going to construct a function R that does not appear in the table. And this proof technique is called diagonalization. So what is this? So obviously it's an element of S because it's a function from the integers to true or false. Now, what is the value of R when applied to an integer J? Well, it's the opposite value of F of J. So R cannot appear anywhere in the table. It is an F of 1 because F of 1 and R give different values when applied to 1. It is an F of 2 because F of 2 and R give different values when applied to 2. And it is an F of 3 because F of 3 and R give different values when applied to 3. So therefore, we obtain the desired contradiction. And we conclude that there are uncountably many functions. We can't give them all integers. And that means we can't compute all functions because there are only countably many programs. Now note that this procedure for constructing R works for any choice of F. It's not just we left R off the list somehow. For anything, any table that someone tries to provide like this, you can always find functions that can't possibly be on it. So quite a remarkable thing. So the basic structure here is that we have shown that there are only countably many programs, right? We can assign them all integers. Like for every integer, I can get a program. But we have functions, mathematical functions, even just the Boolean functions, and there are way more of those than there are programs. So there must be some function that doesn't have a program. All right.
Looks like we have a question, Bruce. One is,
absolutely.
Could you mind, would you mind explaining why R is not in the table again?
Absolutely, no problem. Happy to take questions, and that's what I was hoping to do here. So remember that you can sort of think of this as a game. So mathematically, we say, suppose S is countable, then there must exist an onto function. Equivalently, you, the student, are being skeptical, which you should be. And you're saying, no, I believe they're countable, and I will give you a list of functions, right? And the functions are the same number as the integers. So I'll give you this list here, F1, F2, all the way up. So once you give me that, we can put them in a table like this. Now I get you to certify. I get you to say, are you claiming that your list of functions, which is in order, contains every possible mathematical function? You say, yes, it does. And I say, are you sure? And you say, yes, it does. And I get you to agree that if I can just find one function that's not on your list, that your claim falls apart. And you agree to that. Now I will demonstrate the function. So you give me the list. I write out this table like this, and I construct R. Why is R not on your list? Well, R can't be F of 1 because it disagrees with F of 1 on the value 1. And you can see that here, true and false. It can't be F of 2 because R disagrees with F of 2 on the value 2. And you can see that here. And R cannot be F of 3 because it disagrees, R disagrees with f of 3 on the value 3, as you can see here. So in general, for anything in your list, f of j, R will disagree with f of j at position j, no matter what it is. And so therefore, I've constructed an R that is not on your list, and therefore defeating the claim that the list contains all functions. Does that help?
I have a question about that. This might sound kind of dumb, but if you're trying to say that R can't be f of 3, how is it like comparing to a function that it might potentially be? Like, why would there be a result from f of 3 to compare to if it could potentially be f of 3?
Well, no, I mean, I'm just trying to show it differs from everything on your list. I'm just going down to each one of them, right? So in order to show R is, so you give me this list, right? And then you say, I'm done, right? Then you step back. And then I'm allowed to say, well, and you're claiming your list has every function on it. And I'm saying, no, it doesn't, because I can construct something that's not on your list, right? And you can see that it differs from f of 3 because it differs in the third place, but it actually differs from everything on your list. Did I answer your question? Not a dumb question at all, by the way, but I want to make sure I answered it.
Could you redefine what R is exactly?
So what I did here is I looked at your table. So this is what you give me when you're trying to claim that there's a list of the functions. And what I do is I look at the diagonal here, right? Basically, I construct a function. I look at this true, and I make a false. Basically, I make a function. So the way to think of f of R is that it disagrees with, on place j, it disagrees with f of j. So it disagrees with f of 1 at place 1, it disagrees with f of 2 at place 2, and so forth. You can be sort of almost algorithmic about that. So let's try to write it out in scheme instead. So R is a function, you know, I mean, we can think of this basically R, you know, in some sense R is a function of f, right? It's a higher order function. So what I'm doing here is I'm taking the function you give me, right? So you give me f in this scenario here, right? And what I'm going to do is I'm going to construct my function R from your f, right? That's what I've done here. And now the result of that is a function. So now I can take that and I can apply that to any position j, right? And the way I define this to be not, now you have your function here, you have f of j applied to j. So in other words, your function f is one that orders all the functions here, right? We can also write this more in mathematics. We can say R applied to f applied to j is equal to not f of j applied to j, right? But I think the scheme notation is a little bit better. So what I've done is I've taken your input here, which is your f, and I've constructed a function R based on that. And the key thing here is that it differs from any f in your order at the jth place. Or more graphically, what I do here, given your table, is I construct and I basically look at the diagonal and I just flip the polarity of that. So what I want is that I want R to disagree with f of 1 at place 1, to disagree with f of 2 at place 2, to disagree with f of 3 at place 3, to disagree with f of j at place j. So whereas the diagonal here is true, false, false, true, here I have false, true, true, false. So the key thing about the construction of R is that it disagrees with every function that's in this putative table. And if your function is in the jth place in the horizontal list, then it disagrees on the jth integer instead. Does that help?
Yeah, I think I understand now. It's just a higher order procedure. Oh,
I
function.
mean, you could definitely think of it that way. Yeah. Yeah, that's how I would think about it. Other questions? This is deep stuff, so feel free to ask.
So is this claim based on the fact that the number, that the input numbers are unrestricted? So assuming we would restrict our functions from input, 1 to 100, then of course you could make a complete list of all the functions that are defined for these numbers, right? So it's also kind of based on the fact that we're going into infinity when looking at the functions, right?
We're not actually getting to infinity, but we can get as high as we want. So the functions have to be defined on all the natural numbers. So you're basically right. But remember, we don't actually need to actually get to infinity. We just have to make sure it's defined on any finite value, including as far as you go. But absolutely, to the positive part of what you said, if we restricted this to integers, like the subset of integers 1 to 100, then this proof would not work. You have to have it work on any integers. So great observation. More questions?
There was a question in the chat, which I think is worth a quick comment, which was the set S that you have here isn't the set of all functions.
That's correct.
However, it's sufficient to prove that this set is uncountable, and therefore the set of all functions must also be uncountable.
That's correct. Does everyone see that reasoning? Would anyone like that reasoning explained further? That was a really excellent point.
Yes, please.
Yeah. So here, let me just come here and take you on the off the spotlight a little bit here. So the reason for this is that let's see. So I think I can illustrate this sort of graphically. So suppose that I have a set here, which is the set of all functions, right? Now, if I have a subset S and S is uncountable, then there's no hope I can count the bigger thing, right? Because I proved that a subset of it is uncountable. And that's the argument that was just made. Does that make sense? Do you believe that argument I just gave?
Yes.
Right. I mean, trying to count more things is going to make it more countable, right? So the S is uncountable, right? The subset. Then something bigger is going to be even harder to count. Great question, though. All these are great questions. This is very, deep stuff.
Can I ask a question about the diagonalization argument?
Yep. Sure.
So that argument works for any square that you take of the inputs and outputs. But if, let's say, the number of outputs, the number of functions that you have grows faster than the inputs, like, yes, if you take both to infinity, then there's always a next natural number and always a next function. But for any finite set of natural numbers that you give, you can create a set of functions that does a complete map, because, like, let's say you treated the true and false as binary, any binary sequence can map to a natural number. So it seems like the functions can grow at a faster rate and make it so that there's something below that jth term, if that makes sense.
So, I mean, you're both right and wrong mathematically. I mean, you have a very good insight there. So your first insight is that if you make anything finite, then this proof doesn't work. And that was pointed out by your colleague earlier. But the idea of the functions growing faster, it's a little harder to rebut that, because in fact, the number of functions does grow faster. That's sort of the point. But here we're assuming it doesn't, right? When you assume it's countable, right, which is what we're trying to defeat, then what we're assuming is that there's an onto function from the natural numbers onto S. And that means that the horizontal growth, and this isn't a mathematical term, I'm just trying to give you intuition, the rate of growth horizontally and vertically is exactly the same because it's just the natural numbers. And so, I mean, your intuition would actually, I mean, I don't know what exactly to do with your intuition, but in this case here, the rate is so in the counterfactual assumption, what we sort of assume by way of contradiction is that you're basically going out by the natural numbers here and by the natural numbers here, and that's what it means from F to be a way of counting this with natural numbers. So I think that situation can't happen in the context of my proof, right? Does that help?
I suppose somewhat.
Yeah, I mean, but in a rigorous basis, I mean, think of it as an adversary, is that you can't, I mean, if you think there are more functions there, you can give them to me, give me another table, I'll diagonalize and find something that's not on it, right? And this procedure works for any list of this form, right? To show it's not countable. So for any supposed list, I can find a function that's not on it.
If the list is, yeah, if the list is square into one like that, yeah.
I don't know what it means to be non-square, so I'm not going to confirm that, but because that's not a mathematical term. But I will say that the cardinality of the number of columns and the cardinality of the number of rows is assumed to be the same because they're both covered by the natural numbers. And if that's what you mean by square, then I think we're in agreement. But the point is, if you wanted the vertical dimension to grow faster, and faster was something that was actually mathematically provable, then that would deny my assumption that it was countable. Because if it's growing faster than the number of integers, then that would immediately defeat this. I mean, actually, there is no such list mathematically, but if there was a bigger set in that dimension, it wouldn't have that property. So they're constrained by this. They're constrained in the horizontal dimension by the nature of the integers, and they're constrained in the vertical dimension by way of supposition, assumed by way of contradiction. And if you assume anything else, then you don't have this supposition, and then you're not trying to disprove anything. So you'd be starting with a proof saying, suppose the set of functions is uncountable. Well, I can't diagonalize them, right? But I'm not trying to disprove that they're uncountable. The set of functions is actually uncountable. So I think there's a little logical issue that we deal with. Maybe we take that offline. But I think maybe I've convinced you that this works as shown. Is that right?
Yeah.
Good. Well, let's take it offline. All right. All right, let's do another example that I think will be useful here. So one interesting thing is that, and this was kind of mentioned in one of the comments, we had some really excellent comments. Appreciate them very much. I'm going to spotlight my videos so you can continue to see me while I talk. So we have a name for a function from the integers to true and false, right? We have a name for such things. It's actually called a real number, right? That's pretty neat when you think about it. So if we have one of these strange objects here, like these objects here, a function from the natural numbers to true or false, think of true as 1 and think of false as 0, that's a real number in binary. So this proof directly shows that the real numbers aren't countable, which is kind of mind-boggling. So let's just do that again. We can do it directly. So Gerard Cantor great German-Polish mathematician, discovered this around the turn of the century, 20th century, and he completely flipped out. He turned logic and set theory on their heads. So let's let I be the open interval between 0 and 1 in the real numbers. So these are all real numbers, not floating point, real numbers between 0 and 1. This is going to be the open interval, doesn't include 0 and 1. So I want to say, suppose I were countable. And by the way, our claim is I is uncountable. I want to prove this. By the way, if I want to, let's go back to our argument before and on my little diagram. If I want to show that the real numbers are uncountable, why does it suffice to show that a mere subset of the real numbers is uncountable? Do you see that's the same kind of argument that I had before? Good. So if I show a subset of a set is uncountable, then the bigger set is uncountable as well, because adding more numbers doesn't help you count it. All right, so how would we do this? So proof, suppose I is countable. All right, well, if it's countable, then there exists some function f from the natural numbers onto I. In other words, the adversary gives me a function that's supposed to count it. So given this, I'll construct an element of I that's not covered. So let's just write it down. So f of 1, well, what type is f of 1? It's going to be a real number. So f of 1 is 0.38599055, and f of 2 is 0.2378128, and f of 3 is 0.314159926, and f of 4 is 0.1122112, and so forth. So again, it's the same scenario. What happens here is that I'm trying to claim that I, the open interval between 0 and 1, subset of the real numbers, is uncountable. How do I prove it? Well, by way of contradiction. Suppose I is countable by way of contradiction. Well, if it's countable, then there exists an onto function from the natural numbers onto this open interval. So for any such function, I construct a table like this in my mind, a great big infinity by infinity table. And in the horizontal dimension, these decimals will go all the way out to infinity. And in the vertical dimension, I'll have an infinite number of numbers, each one being put in correspondence with an integer. And so I look at my table and I do the same thing. I construct a number that's different on the diagonal. So for example, I construct a number r that might be something like this, 0.4453, and so forth. So look at r. In the first decimal place after the decimal point, it differs from f of 1. In the second decimal place, it differs from f of 2. In the third decimal place, it differs from f of 3. In the fourth decimal place, it differs from f of 4. So even if someone certified this and had their lawyers sign me a document saying this was all the real numbers, I can construct one that's not on it. So this is pretty wild, right? What we've been able to do here, and this basically, again, turned philosophy, mathematics, and science on its head when Cantor discovered this. What we did is we constructed a real number that's not in the table in exactly the same manner as before. We pick the digits on the diagonal and just make sure that the new real number differs from the ith element of the list in the ith digit, just as we did. So we can conclude, therefore, because the natural numbers, this unit interval is a subset of the real numbers. Since uncountable, we can conclude as a corollary that the real numbers are uncountable. And this means there's no onto function from the integers to the real numbers. It means there are more real numbers than there are integers, actually amazingly more. And again, this is called a diagonalization argument. All right. It's the same argument we had before. If you're practicing your mathematical skills, what you would do is you would notice that a function of this form here is essentially just a binary number. So basically you encode true as 1 and false as 0, and you can see that a representation of a function g is exactly an infinite stream or an infinite sequence of 1s and 0s. And then we would diagonalize on the 1s and 0s in the same way. Here, I've done this in the slightly more natural, although not better, base 10 representation. We have to agree that base 10 representation is actually sufficient to do this. which I think you're pretty comfortable with. But now we have actually shown that there are strictly more, not only strictly more reals than there are integers, but there are a lot, actually it follows that there are a lot more. Okay, so there are more functions than there are programs. So therefore there must be some programs that you can't write. In other words, there's some functions that are unprogrammable. So more functions than there are programs mean there's some functions you might like to have that you cannot write a program to compute. And as a corollary, there are more real numbers than there are integers. Okay. So same proof, different application. Now you might be wondering, okay, I sort of get it, but why would you ever want to compute one of these functions that can't be computed? Like maybe they're not interesting, maybe I don't care about them, maybe you don't. So let me ask you, as we think about this, I'm going to try to just interest you in this next little bit of proof here. And I'm going to ask you, as we think about this, how many of you have ever written a program that had an infinite loop? No one? They're all perfect?
All the time.
All of them, okay. And how many of you have implemented a program that halted with an error?
Many times.
Many times, okay. And not just in Scheme, right? Other programming languages too, right? So wouldn't it be nice if we could do something about that, right? I mean, you know, when I look at this, when I look at something like Racket, which is amazingly better than, you know, what we had before 20 years ago when we were programming, these IDEs have gotten really good. Why can't the program just check? Why can't it say, you know, hey, Vanessa, you're going to have an infinite loop. Don't run that. Stop it. You know, or hey, you're going to get an error. Fix that. That would be really great, right? You wouldn't have to grade anything. So that would be really great if we could do that. And I think you can see that such a feature would be really great. And we would have that thing and we'd put it right into Racket, and you know, programming would be much easier. But there's many, so in other words, there are actually many interesting questions about programs. Like, in other words, we have to be able to take programs as inputs to our function that are going to be, you know, uncomputable. So here's one, and I've written it out just so you can see it really clearly. Here's a program we would like to have. It's called safe. It's a predicate, right? So, and this is a specification. I have not written safe. Let me be very clear about that. I've not written it. I've just given you a specification and said I want it. This is a shopping list expression of desire, not expression of execution. So what safe does, it takes in a program, i.e. it takes a procedure, and it takes an argument. And it returns true if the function call prog of arg will halt with an answer. In other words, no infinite loop, no error, just some kind of answer. It returns false if it doesn't. So this would be super useful if we could have this function. Like we could use it to find infinite loops or programs that get errors and so forth. So I think you'd all agree that would be really nice if we could have such a thing. But there's an issue, there's a problem. So consider the following program that I've written using safe. Now, let me help explain this because this is hard even for native speakers. So we have, what this function does, it's not a useful function except for doing my proof, but what safeify does, safeify in English to an English ear sounds like it's to make safe. So safeify takes some input, namely P, and it in some sense makes it safe. That's the reason for the name. But the name doesn't matter. What really matters is the behavior here. So this is a pretty interesting program here. Now, let us assume that safe exists. And what I mean by safe exists, let me assume that you could write the function called safe, and it would behave as per the spec that I've given here. So assume that safe exists, which means I could write it. So given that safe exists, it must be that safeify is always safe on any argument. Why? Well, because it uses safe to check whether the computation is safe. And it only does the computation if it is. So therefore, safify must always halt with an answer. So we just proved that by my argument, but basically this is substitution model. There are two cases. Either the function p is safe when you run it on p, or it's not. If it's safe, then the function safify runs it on p and flips the answer. If it's not safe, it returns false. But the key thing is that the computation p of p is only performed if the function is safe. And if we assume that safe exists, then the function safify is always safe on any argument. So this is, just to clarify, on any argument. Safify must always halt with an answer. It means no matter what the argument is, safify halts with an answer. All right, so that seems pretty useful. You can make something here. And this kind of makes sense in a way. Let's do a little exercise. What do you think, here's a function. What do you think happens when I call safify on the function lambda x4? What does this return? You may assume safe exists for this purpose of this. So what is this? What do I get when I do this? Assuming safe exists. No, not 4. Use substitution model. You're on the right track. So how would you use the substitution model to figure this out? What would you do?
4.
Kind of. What answer do you get when you do that? By the way, this is not supposed to be a hard or tricky question. This is just to get us comfortable with the idea of safify doing something.
Hashtag F or false?
Yeah, it returns false. Hash F. Does everyone see why that is? Or would you like me to go through it?
Please go through it.
Sure, no problem. So I'm just going to do this using substitution. So first of all, I claim that this follows, if you want, the proof of this is that we assume safe exists and we do substitution model. That's how we know this fact. Now, how do we know that this returns false? Well, safify lambda x4, I'll just write out some of these steps. What this is, so we know that lambda x4, right? We know that this function is safe and applied to anything, right? You can apply lambda x4 to anything as long as it has a value. So this is going to be equal to not lambda x4 applied to 4, right? Applied to lambda x4, right? I'm just using substitution model here. We're just expanding this line here. So not lambda x4 applied to lambda x4. And as was discussed before, that then is equal to not a 4, which is equal to false. Okay, are we good? Any questions about that?
How does applying the lambda x4 to itself give you just 4?
Yeah, so let's do substitution model. So let's just do this in a little more detail here. So first, our function p is going to be equal to procedure x4, right? Are you with me?
Yep.
Now, this procedure is safe. I can apply this to anything, and it's going to be fine. So that means, looking at our substitution model, that assuming safe exists, that this clause here is going to return true, and I merely have to evaluate this clause here. So let's just use the substitution model, which I've abbreviated up here. So that will be not proc x4 applied to proc x4. Right?
Yep.
So how do we evaluate a thing like this? Well, that's not, so we have to instantiate the body. Well, the body doesn't even use the argument, right? So the body of this is just 4. So this is just the value 4, which is 4. So remember how you apply a procedure. You instantiate the body of the procedure, which in this case is just a literal 4, with the actual argument, which is this entire procedure here, substituted for the formal parameter, which is x. But the formal parameter x doesn't appear anywhere in the body, so you just get 4. So this gives you back not 4, which is false. So it's kind of a weird example, but the point was that you actually return a value. Does that make sense?
Yes, thank you.
Okay, good. Thank you for asking. Good.
What if the function takes more than one argument?
I don't need to deal with that I'm just trying to prove, I'm just trying to get a contradiction. Well, then it wouldn't be safe, I guess. I think I actually can answer your question. So if the function takes more than one argument, then it wouldn't be safe when we called on a thing of one argument. So you'd return false. Does that make sense?
I think so, yeah.
Yeah, thanks. It's interesting. No one's ever asked that before, so I needed to think about it. So it's a good question. So it's true that it's covered under this because it's the wrong number of arguments, which would be an error. So therefore, safe would return false, and therefore the procedure would return false. So great question. Had not thought of that. Any more questions? All right. Let us move on to our proof a little bit here and see how this goes. Think about it. So we now see that this weird thing has some, behavior we can kind of understand mostly. And we did a little substitution model here. So this was fine, right? No problem. So in other words, safe existing didn't cause any problems for us. Like, we don't know that safe exists, but if it did, it would return a value. But what happens if I call safeify on itself? What do I get here? What does this return?
That would be not safeify is safeify, right?
Yeah, that's exactly right. Which is kind of puzzling, right? And that's our contradiction. So the claim is that safeify is equal to not safeify. But the problem is that in scheme, there's no value that's equal to its negation. So this is a contradiction. And therefore, safe cannot exist. So the question I have for you is, do you believe your colleague's comment that if you do this, that the value of safeify must be not safeify? Or should we go through the substitution model to understand that?
I'd like to point out that this works if we know that safeify terminates.
We do know that. Oh, I'm sorry, and you agree, Alex, right?
Yes.
Right. Yes. So let's go through that. It's a totally great point. So here's my argument. So basically, your colleague jumped in very nicely and said this answer, but let's try to see why that was and incorporate Alex's comment as well, just so we can see it. And by the way, I'm going through your proof now, so jump in, and if I get it, something you didn't mean, tell me. So here's what Alex said, is that I'll just use S. So safe applied to safeify this is by definition safe. And why is it safe? If the predicate safe exists, then safify must always halt with an answer on any argument. And any argument includes itself. So safify is by definition safe. And we just proved that up here. So because safify is by definition safe, therefore, this line of code has to return true if safe as a predicate exists as a scheme function and is correctly implemented to spec. If that returns true, then what our function must return is not P of P, which by the substitution model is not safify. Remember, our original call was safify. So basically, we have the situation where S applied to S is equal to not S applied to S, which is a contradiction. So there's no scheme value equal to the negation of itself. And the only thing that we assumed here was the existence of safe. That's all we assumed, that this thing here exists. And so therefore, there cannot be any procedure named safe. And this is Turing's halting theorem. So it's a really interesting thing that none of the really neat tricks that we've taught you can help with.
So I had a question about the not safe, you can't have
Sure.
a value that it's not itself. Let's say I extended scheme and I created a value where I just defined it into existence that not x is equal to not x, right? How this might be just a completely wrong question, but like how would that then disprove this, or like, because is this just limited to scheme as it currently stands, or like what would stop me from doing that?
I don't think I understood your suggestion, maybe because you broke up a little. Can you tell me what you wanted your extension was supposed to be again?
Sure, yeah. So I just define a value, let's call it x, where not x equals not x.
But that would be an inconsistent, I mean, that wouldn't be any programming language.
Okay.
Because
So,
in that
okay.
in that programming language, if you give me a programming language where both x and not x is true, then I can derive anything.
Okay.
So that you can't actually use it for programming. So this is
Okay.
mathematics, right? So basically, we're saying this is the same as saying that, we're in mathematics, we're saying this is the same as saying x is equal to not x. It's the same as saying 0 is equal to 1. They're all the same contradiction, right?
Okay.
So it's basically defying a fundamental rule of mathematics. That's the contradiction we're getting. So it's like the proofs we did before, where we showed that 2 is equal to 4, right? It's like that. So there's a good question. We're only proving this for scheme, but there are theorems saying that scheme is universal, so it's equivalent to every other programming language. And that's called the Turing-Church-Rosser theorem, basically, that all these programming languages have the same power. They might have different efficiencies, but the same power. So this is in scheme, but it applies to the lambda calculus. The lambda calculus is equivalent to any programming language. So great question, and very deep philosophically too.
Thank you.
Sure.
So, I have a quick question. So I was thinking
Sure.
of, well, I could, define any function, whatever test that was basically just safify without the predicate. So it was just like not P of P. And is the reason why that would not like cause, problems that like my P of P would never, it wouldn't be safe, like that it would, it would just infinitely loop. But in this, we've assumed that it wouldn't by use of like the safe predicate.
Let me see if I can rephrase your question. So going back to this, you're thinking of taking the not away?
No, I was thinking of taking the line that just having just define satisfy lambda P function, not PP. Just ignore, not have the safe predicate at all.
The issue is that something, well, there are a couple of issues here. So basically, the issue is that I think the issue is essentially infinite loops, right? Is that
Okay.
The way to think about that is that not applies to anything that's of value. The way we handle that in semantics is we imagine that there's this value, which is sometimes written as bottom, the turnstile. And this symbol is what you imagine a function returning. It's like an exception when you get an infinite loop or you get an error. And what's nice about it is you don't have to say there's an error and write it out. You just have this be its value. But the thing is, it doesn't follow the rules of other values. You can't not it. So the way to think about it is imagine I have an infinite loop, right? Imagine I have, f, which returns is an infinite loop, right? And so you can think of f as returning this bottom. But if I had not f, right, that wouldn't return not of bottom. That would also return an infinite loop because it would loop forever as well. So I think the main thing is that when you make these strange constructions, all I can say is it doesn't give me my proof. I can't say that it necessarily, without thinking about it, whether or not it has good or bad behavior. But I think the infinite loop would be the problem. I definitely wouldn't get a proof from doing it.
Okay, cool. And
Great-
then, of
great-
course, the
great
reason this
question.
works is because we've defined safe that it won't make an infinite loop.
Yeah, we have the safe in there to check it. It only does the computation if it's actually safe. Yeah, great point. Yeah, so this would be really nice. So there are lots of functions we'd like to have, lots of really useful uncomputable functions we'd like to have, right? This is just one of them. So this one could be used to find infinite loops or bugs in programs or errors. We'd like to have it in the interpreter or compiler. So we're going to explore more functions and see what's computable and what's not in future problem sets and so forth, like problem set 4 and so forth. So that'll be pretty interesting. Let's just do a little bit of thinking about this. So what I wanted to mention is that Alan Turing, he was actually interested in whether a brain, be it my brain or your brain or a computer brain, could understand another brain. And that was really his motivation, because he not only kind of invented mathematical computer science to some extent, he also kind of founded artificial intelligence. So let me just pose this to you as something to think about a little bit. So if we believe the brain is a computer, this could be like asking if a computer program can answer questions like the halting problem about another program. So the question for you is, if you believe the brain is a computer, do you believe that this halting theorem can circumscribe how well a computer or a brain can understand another brain? In other words, if I can't even in an automated fashion look at a program and decide whether it halts, how can I understand a program that's running on wetware, which is also some kind of computer? So he was really quite interested in that question. So you might think, well, I don't need to, like I'll just reason about it. But there are initiatives now called, for example, the Brain Mapping Initiative at NIH, where they're getting lots of data from optogenetics and signaling and so forth to try to map the pathways in the brain to effectively map the circuits that we can deduce about neural processing. And then the question we're asking is, well, what program is running on those circuits? And it could be that asking whether or not a scheme program halts or not, which we've shown is undecidable, might be equivalently difficult to asking what program is running on a brain that we're mapping using advanced imaging technologies. So this is a super interesting question at the intersection of philosophy, mathematics, and neuroscience. Namely, to what extent does our limitations in understanding what programs do, how do they circumscribe what happens with an actual brain? Okay, let me just sort of summarize some things that I think are worth taking away here. And I've written these down because I think they're worth, maybe saving as a screenshot or something. So in doing this, there really are two new proof techniques today: dovetailing and diagonalization. So as you progress mathematically, you want to try to find ways to tell them apart. Don't confuse them. So mostly diagonalization is used in proof by contradiction. But dovetailing is usually not. It's a constructive strategy to show something exists. So for example, we use dovetailing to prove the rational numbers are countable. We use diagonalization to prove the set of all functions is uncountable. And we use diagonalization to prove that the real numbers are uncountable. And then, of course, at the end, not using either of these techniques, as we showed you an explicit counterexample, namely a function, which would be contradictory to compute. So it's an explicit counterexample to the claim that everything is computable. So different kind of proof in some sense. We want to get better at using these techniques in other places, and we will too, but we're also build on our knowledge of the halting problem to try to understand what's computable and what's not. But let me mention the power of this technique. So, if you spend time doing other kinds of sciences, right? If you say to your professor in chemistry or biology, tells you to do something and you say it can't be done, I mean, you probably would be fired. But in computer science, you may be asked to do things and you can prove that no such computer program can be written. And we have this incredible power because of the clarity of the semantics and our proof techniques. So just keep in mind that this is different from someone saying, quantum mechanics is intractable, which means it's hard to understand, or the brain is difficult to understand, or I have no technique for doing this particular assay in biology. What we're saying here is safe cannot be written to the spec that I gave. It absolutely cannot be written no matter what kind of computer, no matter how long you wait, anything like that. So in some sense, we have a way of being able to say before we try to write it to our boss or to ourselves if we're giving ourselves specification, what are the far reaches of what is computable and what is not. And remember, computable means can you write a program to do it? So this is really quite remarkable that we have that kind of clarity and that we can get to it in sort of 13 lectures. Okay, so that's what I wanted to talk about today. A preview of what's next. We're going to do more on the halting problem, and eventually I'm going to show you a recipe for doing proofs about programs like this, halting problem questions, computability questions. But we don't quite have the tools to do it. So I want to teach you some more about functions and set theory in mathematics, which is also useful for probability and for all sorts of other things. So I'm going to start telling you more about set theory, functions, relations, that kind of thing on Wednesday. So we've done some of that so far, but we've basically gone about as far as we can without learning some more of those fundamentals. Once we have those under our belt in a few lectures, I'll be able to show you a recipe that handles almost all of the halting problem computability questions that you'll see in computer science for the next few years. But we need a little more math to do that. Not difficult math, but there's some foundational stuff. So that's what we're going to be doing. But now you can see the kind of remarkable things that we can prove using just what we had now. We needed to have our techniques for substitution model and lambda calculus and so forth, and rigorously understand what contradiction means. But at this point, we've been able to prove completely rigorously the theorem that Alan Turing used to basically turn the world on its head, his halting theorem, which is a mathematical high point of some people's undergraduate experience, but certainly this course. So that having been said, I want to tell you that I'll stay around for a little bit and I'll take questions if anyone would like to talk more about the halting problem or related things in class. So that's the end of the lecture, and now we'll do some discussions if you would like to talk to me. Thanks very much. Does anyone have any questions or want to discuss anything?
Oh, sorry, go ahead.
Thank you. I was just really quickly wondering if